Welcome. We're going to continue with chapter 10 by looking at what are called isomorphisms of a graph. Now, this is a classic problem in graph theory, and to be honest, it is still fully unsolved. Your book is going to treat it as if it is as something out there, but it's actually an unsolved problem that if you can figure out how to check this in polynomial time, you will win some massive awards and be really, really famous. So let's talk about what is isomorphism in a graph. So two graphs are isomorphic if, in other words, they're the exact same graph except for the labeling of the vertices and edges. That means they're of the same form. So just to give a quick example, I'm gonna make a super simple example. If I do this, 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 and this, and I label this A, this one B, this one C, and I do this graph over here, label them D, F, and H. So if I do this, you can easily see that these are actually the same exact graph. I just changed the labels. Now, I know that this is over redundance, but what happens if I start adding more vertices? What if I have another vertex out here, and then I have another vertex that's in here? Are these the same thing, even though this could be, let's call this J, and this one K? These are still isomorphic graphs, and there's ways to show it by showing that the relationship between HK and AJ and all the relationships, that HK, it has an exact same relationship. Each relationship has a perfect mapping. In this way, the graphs end up having a nice one-to-one kind of thing going on, and that's the key aspect of what we're trying to look at. So that's what it says it's trying to say here is that match up the vertices, and then the edges also have to match up by the same function that we're using. So G's an isomorphism isn't if and only if the vertices and edges can be matched up by a one-to-one function, such a way that edges become corresponding vertices corresponding to each other. Okay, so let's just kind of look at this. Can you show that these two graphs are actually isomorphic? In other words, we need to match every single vertex in G to G prime. That's what this little thing over here is. This little tick is. It's called G prime. So like V5 here, where does that match up? Well, it turns out that this graph, if I was to take this portion right here and slide it out, I could flip it out and do it. And this goes back to the fact that when we draw graphs, we don't have to draw them with perfectly straight edges. We can curve them. We can do all sorts of other wonderful things. And this actually is part of what ends up giving us so much power. So if I even took this and just redid it, so I have so I got V's over on the left-hand side, and so this would be, I'm just going to write the vertices. This is V1, this would be V2, this would be V5, this would be V3, and this would be V4. Make that vertices bigger so it actually works. Now, if you look at it real quickly, you can kind of see the relationship. W5 and V4, these two are related. Then obviously these edges, this edge is related to F1, this edge is related to F2. By the way, those two edges, I could have swapped them and it wouldn't have mattered. You still would have had an isomorphism. And this is the process by which we can kind of work our way through it. So there's a lot of things about this that we can kind of work on this problem. So what we literally have to do is just work through them one by one. Notice that E2 and E3, these edges are parallel with the same endpoints, which means they can they can have the same endpoints that also have to have parallel. So I'm looking over here. I'm like, okay, where's there also a double edge? It has to match up. This vertex, notice it has four edges coming out of it. What other vertex has four edges coming out of it? Only V1. So W2 has to go to V2 and its corresponding edges have to match up. That's the idea between how we can kind of work our way through this. And then we sit there matching one and one and one. And hopefully you're starting to realize that's part of what makes this problem a challenge. You have to run through every possible combination of the mappings to figure out which one actually works. And there's some things that kind of play out and let us make it a little bit easier. There's some that don't. So like here, the only vertex in G prime that has four edges coming out of it is W2. That's how we knew that V1 went to W2. So we end up with this was the edge, the vertex matching. This was the edge mapping. V1 went to W2. We already talked about that one. V2 went to W3 and V3 went to W1. So let's come back here. V3 V3 to W1 right here. V4 then would have to go to W5, V2 to W3, V5 to W4. Boom, we got that. And then the edges match up accordingly. Notice that every edge goes to, not only is it a function, it is a one-to-one and onto function. So it's even more powerful. So isomorphisms are really great. Now, this is actually gets us into some different properties. One is called an invariant of graph isomorphisms, meaning if you have a graph that has some property and it's isomorphic to another graph, then that other property must have the same its isomorphic graphs must have the same property. And that isn't a really important thing. There's a lot of properties that are invariant for graph isomorphism. One of them, well, actually, here's 10 of them on this page. They're ones that we've already talked about. One, it has n vertices. Two, it has m edges. Three, it has a vertex of degree k. It has m vertices of degree k. So not only does it have to have all the same vertices, so this is where that degree sequence idea I mentioned in the other video, really, really useful for these things. If their degree sequences do not match, then these things 3 and 4 automatically fail. It has to have a circuit of length k or a simple circuit of length k. In other words, if it has a circuit of length k in G, it has one in G prime. Same thing for a simple circuit and the number of simple circuits. Is it connected? Well, that's an easy one. If it's not connected, then we just throw it out. Is it Eulerian or is it Hamiltonian? Those are two really important things. A Hamiltonian cycle is really, really critical. Again, we refer to them Eulerian. We call those circuits because we're allowed to reuse vertices. However, in a Hamiltonian, we're not. So quick reminder on that. We're just trying to see if it holds. So let's look at these things. Are these things isomorphic? Yes or no? Pause the video and think about it for a second. See if you have an answer. All right. So if you look at this, there's a couple things that kind of give away that both them are not. First, let's come over here. How many edges are in this graph right here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Oh, the number of edges do not match up. Therefore, we throw it out. If we went here and we counted our edges, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. Okay, we still have 7 and 7. That looks great. Looking at it, I get triangles and I got 3 triangles and 3 triangles. It's all looking great. However, one thing that we don't notice here, again, and vertices, I have 5 vertices in both of them. So look, this has a vertex of degree 4. Where's my vertex of degree 4 down here? Doesn't exist. So therefore we can throw it out. So those are a couple things that we can kind of use. So on simple graphs, now a graph is simple if it has no loops at all. And there's at most one edge between them. So in that case, it becomes really easy to do isomorphism between just the vertex set. We just do the vertex set because the edge sets automatically comes with it. So these are two simple graphs. Are they isomorphic? The answer to that is actually, so let's just go through it. How many vertices? 4 and 4, check. How many edges? 1, 2, 3, 4, 1, 2. Believe it or not, this one has 4. And as we play through this, we start realizing what the isomorphism is. Namely, the isomorphism is going to take B. Notice it's kind of this pendant thing hanging out here. We're going to get to that. It's going to actually connect to W, which is also just kind of hanging out. And then notice that X, Y, and Z form what is called a clique, a complete graph on three vertices. And so here, these form a complete graph on three vertices. However, because A is the one that links up to B and Y is the one that links up to W, then these two have to be connected. So A has to go to Y has to go to A, B has to go to W. And then I can actually pick either one of the other two, and it does not really matter. I will still get the same result. So using this, we see that we can write out this thing right here. And then our four edges, it's very easy then because A is equal to Y, sorry, A maps to Y and B maps to W, then the edges match up beautifully. And that is how you do graph isomorphism. But realize as these graphs grow, it's really, really hard to find isomorphic graphs. This is a massively open problem. It was thought recently to be solved by a famous computer scientist just a couple of years ago. Fortunately, it was then shown a flaw in his proof, and so we're not quite done yet. But this is an open problem if you can find a polynomial algorithm that will compare two graphs and then identify whether or not they are actually uh, isomorphic. Because graphs grow factorially. That's the real reason why. All right, good luck. Let me know if you have any questions about this section.